Hello students, welcome to the amazing platform of Physics Wallah. Welcome to the PW English channel, my dear students. I hope all of you are excited. Today we have reached on the chemical kinetics lecture 4. So today, till now we have discussed about the different orders of reaction. We've calculated the integrated rate law for a zero order reaction. Also we've calculated the integrated rate law for first order reaction. So we'll continue this particular part and then we'll be discussing a lot of new things as well. I hope all of you have revised your previous lectures. So now let's start the amazing session. So what are we going to cover today? We'll be covering Arrhenius equation. Before Arrhenius equation, my dear students, we'll be covering two important topics. Let me write those as well. Let's say this is 3, 4. We'll be covering, my dear students, a pseudo first order reaction. And also we'll be discussing about the nth order reaction. We'll calculate the integrated rate law for a nth order reaction so that we can use that general formula and calculate the integrated rate law for any order, right? Yes. So let's start the amazing session. Before that, I hope all of you remember the integrated rate law for a first order reaction. What was the integrated rate law for a first order reaction? Just let me tell you. The time is equal to 2.303 upon K log A naught upon A naught minus X. I hope all of you remember this particular part, right? Yes. So now my question to you is, we know this rate law. Okay, I am very clear with this rate law. I don't have any issues with this. Now, my dear students, what if, now here A naught and A naught minus X actually are concentrations? Yes. What if we don't have concentrations? We have a reaction in which we have all the gases and we know the partial pressures of those gases. How will we calculate the integrated rate law? That we are going to discuss today. Before that, let me just see the temperature. I am feeling a bit warm. Okay. Okay, perfect. I hope it's on now. Okay, my dear students. Now let's start the topic. Okay, so imagine you have something like this. I'll make you understand this with one particular question and then we'll solve the other question as well. So let's say you have a reaction like this and all of them are gases. This is also gas, this is also gas, and this is also gas. Okay, so now my dear students, if P initial is the initial pressure of the reactant, if P initial is the initial pressure of the reactant and P total, PT is the total pressure of the at some t time from the start of the reaction, show that the rate constant K is given by this particular expression. So how you are going to approach such types of questions, I'll just make you understand. Now, since these are very big products, let me say that this is A reactant which gives you B product and C product. Okay, so A denotes this, B denotes N2 and C denotes C6H14. Okay, yes. So can I say that, my dear students, A gas is giving you B gas plus C gas, right? Yes. Now if we start the reaction, if we talk at the start of the reaction, that is at time t is equal to 0, you had all the reactant, you will not have any product because no reaction has taken place. This means that, let's say that Pi is the initial pressure and the initial pressure will only and only be because of the reactant gas. Okay, so this is your P initial. You will not have any of the products formed till now. Perfect, no issues. Now imagine at some t is equal to t time, my dear students, obviously some amount of products are formed, so obviously the reactant's partial pressure might have decreased. Let's say the pressure decreased is P initial minus X. Okay, so X amount of your B gas would have been formed and X would be, let's say X is its partial pressure. Now this will also be X. Yes, we see the stoichiometry, we write it according to the stoichiometry. Okay, it is given to you at t time, my dear students, the total pressure in the container is PT. Okay, yes. Since the total pressure will be because of this gas, and this gas, can I say that the PT would be equal to the partial pressure of the first gas, which is P initial minus X plus X plus x, my dear students? Yes, we can say that. Let's cancel x to x. So from here, we can say that P total is equal to P initial plus x. Okay, so this is an expression that we need to remember, or we need to just keep in mind while solving this particular question. Okay, so I know that P total is equal to P initial plus x. Okay, and I know that the initial pressure is P initial. Yes, till now everything is clear. If you write the integrated rate law for a first order reaction, what can you say? I can say that according to the integrated rate law, K is equal to 2.303 upon T log. Now, my dear students, initial concentration, now we don't have concentration, but we have partial pressure. So initial partial pressure of the reactant divided by, my dear students, the final pressure of the reactant only. So the final pressure would be P initial minus X. So this is the integrated rate law we have found out in terms of the pressure of the gas. Okay, perfect. Now, this is your law. But till now, what you were asked, you are not able to derive that till now. But if I say that this is equation 1, then can I find out the value of x from the first equation? Yes, I can say that x is actually equal to P total minus P initial. Right? Yes. Now you have to incorporate this x value into this expression. Okay. So let's try to do that. Your K will be equal to 2.303 upon T log P initial upon P initial minus P total minus P initial. Okay. So your final expression would become K is equal to 2.303 upon T log P initial minus P total, minus would be plus. So P initial upon 2P initial minus P total. Okay, so this is the final expression that you have derived for the rate constant in terms of partial pressures. Okay, yes, let's see, was this the expression we needed to derive? Yes, 2.303 upon T log P initial upon 2P initial, and this is P. Right? Yes, perfect. Yes, we have derived this particular expression here. So the basic idea, what I want to tell you is everything is exactly same. You have to write the integrated rate law just in terms of pressure this time of the reactant. Now, you cannot leave the expression in terms of x. So what will you do? You'll find out the x value from this expression, and then we'll incorporate in this. And every question is going to be solved by the same steps. So you just need to understand one part and you will be able to do the other part yourself. Okay. Yes. Perfect, my dear students. Write it down and then we'll move forward. Okay. I hope you've written this. Now let's move forward, my dear students. Next. The next question is on your screen. Try the question yourself. I'll also help you. Don't worry, but you have to try it yourself. So the question says that you have A is also gas, B is also gas, C is also gas. It says that initial pressure is P initial and total pressure is P total. Give the final expression. Okay. So exactly the same question. How are we going to do? Let's try. I hope you've paused the video. You've tried the question yourself. Now we'll be doing this question ourselves. So you have A, which goes to 2B plus C. Okay. So now let's say initial at T is equal to 0 time. It is P initial pressure. There you will not have any form of the reactants. Now at some T is equal to T time, let's say P initial minus X might have reacted. So 2X would have been formed and X would have been formed. We are writing according to the stoichiometric coefficients. Okay. So now, my dear students, using the integrated rate law, first let's say P total will be equal to the partial pressures P initial minus X plus 2x plus x. Okay, so x cancel. So P total is actually equal to P initial plus 2x. Okay, yes, from here, can you calculate the x value? Yes, you can calculate. So 2x will be equal to P total minus P initial, and your x value would be P total minus P initial upon 2. Okay, yes. This is the value that we have till now derived. I hope you're clear with this. I hope you don't have any issues till now. Now let's write the integrated rate law. Let's write the integrated rate law, my dear students. K is equal to 2.303 upon T log, in terms of partial pressures, it would be P initial upon P initial minus X, right? Yes. So K will be equal to 2.303 upon T log P initial upon P initial minus, let's say, what is the X value? X value now is P total minus P initial upon 2. So this would be P total minus P initial upon 2. Okay. So this would be equal to 2.303 upon T log 2P initial upon 2P initial minus P total. This would be whole. So this would be plus P initial. So K would be equal to 2.303 upon T log 2P initial upon this would be 3P initial minus P total. So this is your final expression. This is your final expression. Were we supposed to derive this? Let's see. Okay, we have to give the final formula. So let's see which is the correct option. 2P initial upon 3P initial minus P total. 2P initial upon 3P initial minus P total. Option A is your correct answer. Option A will be your correct answer. So this is how you will be solving the questions if you are ever given only the gases in the first order reaction. How are you going to use that? I have told you. You have to follow the same steps and you'll always end up with the correct answer. Okay, perfect. If you want to write it, just pause the video, write it, and then we'll move forward. Okay. Now, my dear students, we'll be starting another topic, which is your nth order reaction. We've discussed zero order reaction. We've discussed first order reaction. We can discuss second, third, fourth, but now we'll be using a general formula and we'll apply that formula to all the order of reactions and we'll be good to go. Okay. So now, my dear students, how are we going to solve this? The first, all the steps are exactly same for as we followed for zero order and first order. So now we only have to use the same steps. Okay. So what was the first step? We have to consider a reaction. Let's say you have a reaction A goes to B and it is a nth order reaction. Okay. So if it is a nth order reaction, then can I say that from the rate law, rate will be equal to K into A raised to the power N. We can say this. Yes, ma'am. Perfect. It's absolutely right. So let's say this is your first equation. Second, my dear students, we'll be calculating the instantaneous rate. The second step always was to calculate the instantaneous rate. So the instantaneous rate would be R is equal to minus dA by dt. This was the instantaneous rate, right? Yes. Let's say this is your second equation. Now, since we are talking about the same reaction, obviously both of the rates will be equal, right? Yes. So can I say that? One will be actually equal to 2? So let's just equate both of them. Exactly same steps, right? Yeah. So K A raised to the power N is actually equal to minus of dA by dt, right? Yes. Now we'll just cross multiply. So when we'll cross multiply, it would be equal to K into dt would be equal to the minus of dA. I can incorporate this negative here. This would be dA by, no. Yeah, this would be A raised to the power N, right? Yes. Till now everything is clear. Perfect. Let me just put a line here. Now, my dear students, now we have cross multiplied it. Now we'll integrate both the sides. So this would be minus dA by A raised to the power N. And this would be equal to AD. Now let's integrate. So integrating, what will I get? Integrated dA by A raised to the power N from A naught initial to final AT amount. This would be equal to minus K. K is a constant from 0 to T dt. Yeah, I hope you're clear with this. Yes. Now I want to tell you, now when you integrate, my dear students, anything, let's say dx upon x. So the integration is always x. Let's say it has power n. So this would be minus n plus 1 upon minus n plus 1. This is the integration formula we use. Okay. So I'll be using this formula. So I've told you beforehand so that you will not be confused with this. So dx by x raised to the power n integration x raised to the power n integration is equal to x raised to the power minus n plus 1 upon minus n plus 1. Okay, perfect. I hope you're clear with this. Now we'll be using this into this. So your expression will become a minus n plus 1 upon minus n plus 1, right? And the limits would be from a naught to a t. This would be equal to minus k t from 0 to t. Okay, now we have to put the limits, the higher limit minus the lower limit. So now let's just incorporate the limits. You will have a, the first higher limit is, just a second my dear students, 80, right? 80 raised to the power minus n plus 1 upon minus n plus 1 minus initial amount, which is a naught minus n plus 1 upon minus n plus 1. This would be equal to k into t minus 0. So we can say that let's take 1 upon n minus 1 common. So 1 upon n minus 1, no. 1 upon 1 minus n is taken to be common. This is actually 1 minus n, right? Yes. And we can say that a of t raised to the power 1 minus n minus a naught to the power 1 minus n is equal to a t. So this is actually the general formula, my dear students. This is actually the general formula that you need to know about the nth order of reaction, any order of reaction, any order of reaction. There is a note that you need to understand. This particular formula is applicable on all orders of reaction except first order reaction. For first order reaction, you cannot use this formula. Why? Because if you put n is equal to 1 for first order reaction, you will get value as, see, 1 upon 1 minus 1. This is 1 upon 0. This will be infinite, which is not possible. So here, my dear students, you just need to understand that this is the integrated rate law for nth order reaction. It is applicable on all orders, not applicable to first order reaction. This is the only limitation, that it is not applicable to first order reaction. First order reaction we've calculated on our own, so we are very good to go. We don't have any issues, but you just need to understand that you can use this formula for any order of reaction, 0, 2, 3, 4, 5, 6, any order, and you will get absolutely correct answer. But it is not applicable for the first order reaction. Okay, so just make this as your note and you are good to go. Okay, perfect, my dear students. If you want to write it, pause the video, write it, and then we'll move forward. You can write this as well. Okay, perfect. Now we'll be discussing about the another part, and that another part is actually the half-life of nth order. Obviously, we've calculated the integrated rate law and we'll have to calculate the half-life of nth order. Using this formula, you can calculate any half-life of any order, right? Yes. So, can I say that the next topic would be half-life of nth order? Half-life of nth order reaction. So for this, my dear students, you just need to memorize one simple formula. You just need to memorize one simple formula and you are good to go. Perfect. Okay, so let's write it. This would be T half for nth order would be 2 raised to the power n minus 1 upon n minus 1 a naught raised to the power, just a second, a naught raised to the power n minus 1 into k. This is the general formula. This is the general formula for a nth order reaction for the T half, that is the half-life. Okay, so you can apply this formula on any order of the reaction and your answer would absolutely be correct. Except, my dear students, this is not applicable to the first order reaction again. Okay. So again, this formula will not be applicable on the first order reaction. So if you want to write it, just write it. Not applicable on first order reaction. This is not applicable on your first order reaction. Okay, now let's try and understand whether it is correct or not, because I know from the derivations that the half-life for a zero order reaction is A by 2k. Now let's see, is this correct or not? Okay, so if I have a zero order reaction, then n will be equal to 0. Let's just put it. T half would be equal to 2 raised to the power 0 minus 1 upon, you will have 0 minus 1 into A naught raised to the power 0 minus 1 to k. This would be equal to 2 raised to the power 0 minus 1 would be 2 power minus 1. Have minus 1 here divided by, you will have A naught here whose power is negative, and this would be, my dear students, 1 upon 2 minus 1 upon A naught raised to the power minus 1. So I can take it in the numerator part, and this would be k. Let's try to solve this. This would be 2 minus 1. This is minus half. So 1 by 2k. A naught by, there is something which we are missing. Yes, see, 0 minus 1. So here a negative sign will be there. Yes, ma'am. Here a negative sign would be with minus 2, and you will have k here. So negative, negative gone. This would be A naught by 2k. Yes, perfect. Yes. And this was the expression that we actually derived. So yes, this formula is actually applicable on all the orders of the reaction, 0, 2nd, 3rd, 4th. So whenever you are asked for the half-life expression for any order of reaction except the first order reaction, you only have to use this formula. So you just need to memorize this one simple formula. Okay, I hope you're clear with this. Perfect, my dear students. Pause the video, write it, and then we'll move forward. I hope you've written it. Okay, now my dear students, let me give you some homework. So you have to calculate half-life expression, that is T half, for T half expression for first is second order reaction, and second is third order. Okay, so try to do these on your own. This is your homework. Perfect. I hope you're clear with this. Perfect, my dear students. Let's move forward. We'll start another topic now. Now, the next topic is pseudo first order reaction. Okay, so now we'll be discussing about pseudo first order reaction. So first, let me write the heading. So, first order reaction. Okay, so now, my dear students, what does pseudo first order reaction do? So now let's try to understand this. If you talk about a pseudo first order reaction, what does this actually mean? Okay, so for this, you need to understand a very simple thing. Imagine I give you a reaction where you have A plus B, two reactants, they are giving you a C product, and I am saying that it is an elementary reaction. If I say that it is an elementary reaction, then just go to your first lecture where I said that whenever you have an elementary reaction that is a single step reaction, there, my dear students, your molecularity is actually equal to the order of the reaction. And what is molecularity? The number of reactants actually taking part in the reaction. How many number of reactants are colliding? 2. So the molecularity is 2. So the order of the reaction should also be equal to 2. Right? Yes. Perfect. This is what we understand, that since we are given an elementary reaction, we have 2 reactants. So the order of the reaction should be definitely 2. Right? Yes. Perfect. So if it is 2, then it will follow all the rules according to the second order reaction. Right? Yes. But my dear students, what if I make a small change? What change? Let me say that this particular reaction, this B is in excess. And still now it is elementary. So what will you say? You will say what? It doesn't matter. Still the order should be 2. right? Because molecularity is 2, you have 2 reactants. What if the other is in excess? How does that change anything, right? Yes, it does change, right? Yes. See, technically, since you have 2 reactants, then definitely the order of the reaction should be 2, and it should follow all the integrated rate law, the half-life of a second order reaction. But what happened actually was, when experimentally this reaction was studied, it actually was following every rule of a first order reaction. It had half-life according to the first order reaction. Its integrated rate law was according to the first order reaction. But why? What was the reason? It should be according to the second order reaction, right? So now you need to understand here, my dear students, when in a reaction you have a reactant which is in excess. Since one of the reactant is so much in excess that if it is consumed a little bit, it doesn't matter. If it is changed a little bit, its concentration, its amount will not change. It will be nearly constant. How can you imagine this? You can imagine this with this particular example, that imagine I have this bottle full of water, and if I take a drop of water from it and throw it outside, will the volume of this water inside this bottle change? No, it will be a very negligible change, since according to that drop of water, this water is in excess, right? Exactly like if you try to understand that you are sitting in front of a ocean, and you just try to take a bucket full of water out of it, right? Yes, will the volume of the ocean decrease? No, it will be nearly same, because the change is very negligible. Exactly the same way, my dear students, here whenever you have a reactant which is in excess, this means that when the reaction will take place, when the reactant will be consumed, it will be so little that the overall change would be negligible. And that is the reason if we say that the rate according to this order should be K into B into A, and this should be a second order reaction, but it will not happen. Why? Because this is in excess. And since this is in excess, so this overall value will always remain as constant, let's say K double dash. Okay, so the change is so negligible that it is considered to be constant, and your final rate law actually comes out to be K double dash into A. And here we can say that, the concentration which is changing is only because of A reactant. The B change is so negligible that we consider it to be constant. And that is the reason such reactions behave as a pseudo first order reaction. This reaction must have followed the second order reaction, but since one reactant was in excess, it will behave like a pseudo first order reaction. Okay, perfect. I hope you're clear with this. Please write it. I'll make you write this in my own language as well, but just write it before. I hope you're clear with this. Now, my dear students, you can write that in pseudo first order reaction, or you can say that pseudo first order reaction. How can I make you understand that? See, whenever, just let me make a sentence. In pseudo first order reaction, one reactant is in excess. As a result, the change in its amount is negligible, and hence it is considered to be constant. Okay, so the reaction must have acted as a second order reaction, but actually behaves as a first order reaction. Okay. So this is what happens in a pseudo first order reaction. One of the reactant is in excess. Okay. Yes. Perfect. I hope you're clear with this. If you want to write it, just write it. Let's take an example of pseudo first order reaction, my dear students. Example is hydrolysis of esters. These reactions you actually study in organic. The hydrolysis of ester reaction is something like this, that you have a ester, let's say you have RCOOR and you have water here, and this water is in excess. And from here you get RCOOH plus H2O. So here, my dear students, since the reactant is in excess, so the rate should have been something like this. But actually, since this is in excess, so this will be a constant. So R is actually equal to K double dash into RCOOR. And that is the reason this is considered to be a pseudo first order reaction. Okay, perfect. I hope you're clear with this. This is an example of pseudo first order reaction. You can write it and then we'll move forward. I hope you've written it. Perfect. Now, my dear students, let's see some technical terms for this pseudo first order reaction. It says that the reaction is actually a second order reaction but looks like a first order reaction, and this is known as a pseudo first order reaction. If we let the reaction happen without any external changes, the rate is expected to decrease with decreasing concentration of A and B. But actually what happens, B is taken as in excess and its concentration change is not showing up in the reaction. It is nearly constant. Therefore, the rate is decreasing with the decreasing concentration of A only, and that is the reason it behaves as a first order reaction. Okay, I hope you're clear with this. Pause the video, write it, and then we'll move forward. Okay, can I have some water and then we'll move forward? Okay. Let's move forward, my dear students. The next topic which we will be discussing now is your Arrhenius equation. So now let's try to understand what Arrhenius equation is. I hope all of you remember in the initial part, I told you that the rate of the reaction actually depends on four major things. Whenever we talked about rate, I said that it depends on the reactant, the concentration of reactant. Then I said it depends on the temperature. Then I said it depends on the nature of the reaction. And also it depends on the catalyst. It also depends on the catalyst. See, till now we were discussing about this part. That is the concentration of reactant. We calculated the rate law, we calculated the integrated rate law, we calculated the instantaneous rate. Everything and everything was about the reactants, right? Now, this part is done. Now we will be discussing about these three major parts, and this will give you your Arrhenius equation. So Arrhenius equation is actually the equation which will tell us that how rate depends on these three factors. Okay, yes. So it describes the effect of temperature, nature of reaction, and the catalyst on the rate constant of the reaction. Now you will be like, ma'am, why rate? rate constant. You said rate, right? So now, my dear students, when you talk about rate of the reaction, you say this, right? This is the general expression. So this is your rate constant. As your rate constant increases, your rate of the reaction will definitely increase. So your rate actually depends on the rate constant. The more the rate constant, the more will be the rate of the reaction. The more the rate constant, the more will be the rate of the reaction. Right? Yes, perfect. I hope you're clear with this. So this is how your rate of reaction depends on the rate constant. And now these three factors actually are dependent on the rate constant. Sorry, rate constant is actually dependent on these three parts. If you increase the temperature, your rate constant will increase. If the nature of the reaction is changing for different reactions, there will be different values of rate constant. And if you use a catalyst, the rate of the reaction will also increase or decrease depending on what catalyst you are using. So these three factors do not directly affect the rate, but they do affect the rate constant, which eventually affects the rate of a reaction. Okay, and this we will be studying in the Arrhenius. I hope you're clear with this. Perfect, my dear students. So if you want to write it, first write it and then we'll move forward. I hope you've written it. See, now for one important thing which you need to write as a note is, if you ever open your NCERT, which is of utmost importance, you should read your NCERT. There is a line, and that line actually gives you the dependence of temperature on the rate constant. What does it say? It says that with every 10-degree rise in temperature, rate constant increases 2 to 3. So my dear students, with every 10-degree rise in temperature, the rate constant of the same reaction will increase 2 to 3 times. Okay. So if the rate constant is increasing 2 to 3 times, then the rate of the reaction will also increase 2 to 3 times. So as you increase the temperature, the rate constant increases, and eventually the rate of the reaction will also increase. This is a very important line. A lot of times a question is asked from this particular part. So you need to write it with a note. It is important. So write it and then we'll move forward. Okay, perfect. Now, my dear students, let's try to understand what exactly is a Arrhenius equation, right? Yes. So, for understanding the Arrhenius equation, you need not be worrying about from where this particular expression came. In your syllabus, it is only the expression that you need to understand. You don't need to understand from where it came, right? Yes. So, the expression for your Arrhenius equation is K is equal to A e raised to the power minus EA by R. So now let's try to understand what each and every term here. Okay. So here, my dear students, K is your rate constant. A is your pre-exponential factor. Also known as Arrhenius parameter. EA is your activation energy. I'll make you understand this as well. Don't worry. Activation energy. R is your gas constant. And T is your temperature. So these are the factors which are used in a Arrhenius equation. What does each denote? I have told you. K is your rate constant, A is the pre-exponential factor, or it is also known as Arrhenius parameter. EA is the activation energy, R is the gas constant, and T is the temperature. So now let's try to understand what actually I hope you're clear with this K part, you are clear with the T part, R part. Arrhenius parameter is just a constant value, so you need not worry about that. The main thing that we don't understand is what is activation energy. What actually is activation energy? So now let's try to understand what is activation energy. Okay, so my dear students, to understand the activation energy, we need to go again to the that reaction quotient part. I made you draw a graph. I hope all of you remember. We did draw a graph something like this, and where you had this energy profile, and this was your reactant, and let's say this was your product, and we said that this is something as your, for a particular reaction, a reaction that is taking place from R to P, and let me say that it is a elementary reaction. Since it is an elementary reaction, this is your transition state, and this transition state is only one. Since it is one, so we can say that it is a single step reaction, elementary reaction. These were the things which we can find out till now. We also know that reactant has a higher energy, product has a lower energy. Now I'll make you understand what actually is threshold energy. How can you understand threshold energy? You can very easily understand it with the common example which you do every day. Okay, just imagine you're sitting and you're watching TV, right? Yes, you are in your most comfortable bed. You're just cozying around there. And now, my dear students, all of a sudden what happens is your mom comes to your room and she says that, please go to the grocery store and bring some tomatoes for me. And you'll be like, no, I won't go. I am resting. I'll not go. Right? Yeah. This is your first impression. This would be your first, what would we say? This would be your first thing that you will say to your mom. Right? Yeah. Then what will happen? Your mom will say, please go. I'll give you 5 rupees extra. You'll be like, no, I won't go. And then you'll see the opportunity and you will say, okay, fine. If you want me to go, I'll definitely go. But then you'll have to give me 50 rupees extra. And she'll be like, no, I can't give you 50 rupees extra. You'll say that if you'll give me 50 rupees, I'll go. If you won't give me 50 rupees, I won't go. Right? Yes. Now your mom actually will try. You are determined. You don't want to go, and you're like, if I get 50 rupees, I'll go. What matters? I'll get 50 extra rupees, right? Yes. But if lesser than 50, I won't go. This is decided. Okay. So your mom will say, let me give you 30 rupees and please go. You'll be like, no, 50 means 50, no lesser than that. Okay. So this means that you have decided your limit, that after this I'll go, before this I won't go. Right? Yes, this is the situation. Yes, bilkul. So now, my dear students, what happens is, I just spoke a Hindi word. Wow. Again a Hindi word. Wow. Okay. So now, my dear students, what actually will happen is, your mom will because she needs the tomatoes to make food. So she'll say, okay, fine, I'll give you 50 rupees. You'll take 50 rupees and you'll go. Okay. What if your mother is in a good mood and she says, okay, fine, I'll give you 60 rupees. You'll take those 60 rupees and run even faster. Right? Yeah. So this is what is your threshold energy. Those 50 rupees, those minimum amount of rupee that you asked your mom, was your threshold energy. Exactly like that, my dear students. All the reactants before starting the reaction have a particular activation energy, threshold energy. That energy is required for the reaction to take place. If a reactant does not have that much activation energy, the reaction will not take place. That reactant will not react. Okay, let's say you have 10 reactants, and out of them only 5 has the required activation energy. Then the other 5 which do not have the required activation energy, they will not react, they will not form products. Okay, so in the reactants, there are a few reactants which have the activation energy required for a reaction, and there are reactants which do not have the activation energy required for a reaction. So a reaction only happens when the activation energy, that is the minimum energy, which is also known as the threshold energy, is attained by the reactants. And here, my dear students, this is actually, from here to here, is your activation energy for the forward reaction. So this is what is known as the activation energy. So now I can say that EA1 is the activation energy for forward reaction. Now let's say the reaction took place and at one particular point, now I want the reaction to go back. So if I want the reaction to go back, this means that I want the product to go into the reactant side. So this time these products will become my reactants, right? So the reaction will take place like this. So now, my dear students, you will understand the major difference. See, from here to here, this will be the activation energy for backward reaction, right? So let me say that EA2 is the activation energy for backward reaction. Now try to understand this. Imagine reactants have higher energy as compared to products. So reactant wants to get converted into products. So we know that the reaction will be spontaneous in the forward reaction, forward direction. Okay. If I talk about the backward reaction, you will say products are lesser in energy, so they are stable. Why will they want to go to the reactant side? So you need to push them. You need to give them some energy so that they'll go to the reactant side, so that the reaction is not spontaneous, right? And you can explain this in terms of activation energy as well. See, the spontaneous reaction has a lesser amount of activation energy, but the backward reaction is a non-spontaneous reaction and it has a higher amount of activation energy. So the more the activation energy, the difficult would be the reaction to happen, right? Yes. So the reactions which have very lower activation energy, those reactions are faster. They will take place fast, right? Yes. This is how we understand both the concepts. Okay. I hope you're clear with this. Now you need to write the definition. So let's just write the definition. The minimum amount of energy, the minimum amount of energy required by the reactants for a reaction to take place is known as activation energy or the threshold energy. Okay. I hope you're clear with this. Okay, perfect. So now, my dear students, let's write the unit of activation energy as well. Okay, so let me just write it here. Unit of activation energy. Generally the unit that we use for activation energy is kilojoules per mole, or you can use joules per mole, or you could use calories per. Okay, these are the units that are used for the activation energy of a reaction. So if you want to write it, and then we'll move forward. Now, let's understand a little bit more. Before that, my dear students, I just want to tell you one more thing, that what value of R to be used. R value, that is your gas constant value, depends on what unit you are using for your activation energy. If your activation energy is in joules per mole, you will use R value as 8.314 joule per Kelvin per mole. Okay, this is very important. If your activation energy is given in calories per mole, then you will use R value as 1.98 calories per Kelvin per mole, or you can use it approximately as 2 calories per Kelvin per. This is very important because this will be used in numericals. So you need to understand this particular part. Write it and then we'll move forward. I hope you've written this. Now let's move forward, my dear students. let's talk a little about Arrhenius equation, right? Yes, we've discussed about activation energy now. Arrhenius equation is applicable to elementary process and only one-step reactions, okay? So Arrhenius equation is only and only applicable to one-step reactions. Next, since exponential term is unitless, the unit of K and A would be the same. Now, I want to make you understand this part. See, if we talk about the Arrhenius equation, then K is equal to A e raised to the power minus EA by R T. Now, my dear students, this is the exponential part. So, the exponential part, this is unitless. This is actually unitless. So, the unit of K, the unit of K is actually equal to the unit of A. So the unit of K is actually equal to the unit of A. Okay, this is what you have been told because it is an exponential factor, so it is unitless. If you want to write it, write it. Next. It is measured that, it is assumed that Arrhenius parameters, activation energy and the Arrhenius parameter A are independent of temperature. They do not depend on temperature. Okay, this is something you need to understand. Okay, perfect. I hope you're clear with this. Let's move forward. Now, let's understand this. Okay, so now my dear students, what I want to tell you is that unit of K is equal to unit of A. We have understood till now. So now, my dear students, let's see the temperature dependence. Now let's see the temperature dependence. Imagine I have given you a question that what will be the value of K at infinite temperature. If you have increased infinite temperature, if you have increased the temperature to an infinite value, what will happen to the K value? Okay, so now let's try. We know that K is equal to A e raised to the power minus EA upon R. Now, since you are increasing the temperature to infinite, so can I say that this is equal to 1 upon 0? Infinite, yeah. So this would be 1 upon 0. So this would be into 0. So this whole part is 0. So K will be equal to A e raised to the power 0. So K will be equal to A, right? Yes. So from here, I can say that Arrhenius parameter A will be equal to K at infinite temperature. So actually your Arrhenius parameter A, that is your pre-exponential factor, is equal to the maximum value of K, right? Yes, at infinite temperature. So this is something we just deduced, and this is very important. You need to understand this. The maximum K can be equal to A. This is the maximum value for the rate constant. Okay, perfect. If you want to write it, please write it and then we'll move forward. So here it is written that when the temperature goes to infinite, K is equal to A, and the A is called the maximum rate constant. Okay, yes. Now, my dear students, we'll be plotting a graph. Now let's try to plot a graph, right? Yes. So I know that what are we going to do? We are going to plot a graph between ln of K versus 1 upon T. Now let's try to plot a graph. See, I know that K is equal to A e raised to the power minus EA by RT. Minus EA by RT, right? Yeah. So now let's take natural log on both sides. Okay. So taking natural log ln on both sides, what will we get? We'll get ln of K is equal to ln of A into e raised to the power minus A by R T, right? Yes. So now I am using a expression using ln of A into B is actually equal to ln of A plus ln of B. This is the property of natural log that I'll be using. Okay. So now let's try to use this. Ln of K will be equal to ln of A plus ln of e raised to the power minus EA by R T. Now, my dear students, you need to understand this property of log, that using whenever you have ln of e raised to the power something, this is actually equal to x. Whenever you have natural log e raised to the power x, you get the value equal to x. So now I'll be using this. Can I say that ln of k is equal to ln of a minus ea by rt? Right? Yes. This is a very important expression for us because now we'll be plotting a graph using this expression. Okay. So now let's just draw a graph. See, you have ln of k is equal to ln of a minus ea by rt. So let's compare this with the straight line equation. What is your straight line equation? Y is equal to c plus mx. So the y-axis would be ln of k. The x-axis would be 1 upon t. And your intercept would be c. That would be equal to ln of a. And my dear students, your slope m would be equal to minus ea by r. So you have a negative slope and you have a straight line equation. So let's draw the graph. So your graph would be a straight line. This is your y-axis. Y-axis is ln of k. This is your x-axis. X-axis is 1 upon t. And it is a straight line with a negative slope. So this would be something like this. And your slope would be minus ea by r. Right? Yes. This is your slope. And this is your intercept, which is equal to ln of a. So this is the plot that you get between the ln k and 1 upon t. So this is how a few of the questions are asked. So you need to understand how to answer these questions. Okay, perfect. I hope you are clear with this. Please write it, my dear students. Now, I hope you've written this. The other question that is asked is you have to plot a graph. You'll have to try this yourself, okay? You'll have to try this yourself. Draw a graph between log base 10k, log base 10k versus 1 upon t. So this is the plot that you have to draw on your own. To try this, it is very easy. You have gone halfway. You only have to add 2 to 3 lines and you will get your graph. Okay. So pause the video, first try it and then I'll help you out. So how are we going to do this? See, you know that ln of k is equal to ln of a minus ea by rt. Right? I hope you're clear with this. You don't have any issues till now. So now, my dear students, you are going to use a log property using ln of x is actually equal to 2.303 log base 10 of x. Okay. So whenever you have to convert a natural log to log base 10, just multiply it by 2.303. So if I multiply it by 2.303, I'll get 2.303 log base 10k will be equal to 2.303 log base 10a minus ea by rt. So now what I'll do, I'll divide the complete equation by 2.303. Okay. So divide by 2.303. So this would be log k will be equal to log a minus ea upon 2.303 rt. So this is the expression that you will be using to draw the graph. Okay, so now let's try to draw the graph. So let's try to compare it with the straight line equation y is equal to c plus mx. So your y-axis would be log k. Your x-axis would be 1 upon t. Right? And then you will have your intercept c, which is equal to log a. And you will have your slope m, that will be equal to minus ea upon 2.303 r. Okay. So this is what you will be using as your slope. Just a second. Yeah. Yes. So if you want to draw this graph here, the graph would be, you will have log base 10 k here. You will have 1 upon t here. It will again be a straight line. And this time, my dear students, your slope would be minus EA upon 2.303 R. This is your slope, right? Yes. And your intercept would be log A. This would be the graph for your expression log K versus 1 upon T. So this is how questions are asked. I hope you're clear with this. Perfect, my dear students. Today, let's wrap things up. I hope now you can understand this part. The plot of ln k versus 1 upon t provides both the Arrhenius parameters. How do they provide both the Arrhenius parameters? I just want to make you understand. We just did plot this graph, and see, if you find out the slope, you will get EA upon R, right? And if you see the intercept, you will get ln A. These are the two Arrhenius parameters, A and EA, and you will calculate that both of them by the graph, right? Yes. So this is what is told to you in this particular line. Yes. Now, I hope you are clear with each and every part. Perfect, my dear students. Let's wrap things up today. We'll solve a lot of questions tomorrow. A little bit part of your Arrhenius equation is left. We'll cover that. Then we'll discuss about catalyst, and then we'll practice a lot of questions. Catalyst part is not majorly discussed in this part. In this particular topic, we'll be discussing that in the later section, which is your surface chemistry. The minimum part which is required, I'll help you out and make you understand that here. Rest all we'll do in the surface chemistry chapter. Okay, I hope you're clear with this. Today we covered almost everything about Arrhenius equation. We did discuss about pseudo first order reaction. We did discuss about the nth order reaction. We found out a magical formula for the half-life which you can use and calculate the half-life for any order of reaction except n is equal to 1. That is your first order reaction, right? Yes. I hope you enjoyed today's session. We'll meet in the next lecture. Till then, keep studying, my dear students. We'll meet in the next session. All the very best. Thank you so much.